I'm just going to kind of go over the syllabus, let me make sure people know what to expect, talk about academic integrity, before we get to the fun part. First I'm going to go see who else here. So, Ali?
Yes.
Ahmed? No, Ahmed? Xavier is here. Griffin is here. Justice is here. Zach is here. Adam is here. Alan is here. Naveen is here. Wes is here. Mukti is here. And no Samuel. Okay. There's no text for this course. And that's why you have the really big packet of, those are practice exercises. Most of that document, like more than half of that document, is actually just the worked out solution. So it's not just answers there's full solutions to most of the problems. Those are practice. They're not to turn in or anything. I will assign practice exercises each day, like I'm doing today for the logic stuff. And then we'll have assignments that will be turned in for a grade. So let's just kind of go through this. There's my information. Please call me Rachel. And then we'll have lecture notes, kind of like if you've ever taken a course with me before, like we'll have a packet for each chapter. I'll hand that out fresh when we start a new chapter. I do recommend a TI 83 or 84. It's possible to get by with a scientific calculator. There's a lot of this class we don't need a calculator for at all. I don't imagine we'll really need one until, sorry, hold on, like chapter 4. Like I just don't think probably won't need a calculator at all until chapter 4 for the most part. But we can't use a TI 89 or anything with a computer algebra system because it takes all the fun out of it. So we start our first unit, the first 3 chapters. We do some propositional logic, and then we do some set theory, and then we kind of examine what those things have in common when we look at Boolean algebra. And then we go through and we do other stuff. We do some looking at functions and relations. We do some number theory, and then kind of develop techniques of encryption. We kind of look at number theory and RSA encryption. We do some matrix encryption. Most of this course is like the work you're going to do to turn in is stuff that you take home to work on and turn in, like assignments. And then when we have our tests, there'll be 2 tests. Each test has 2 parts. So there will be like an in-class part of each test that's going to be more computational, and then a take-home part of each test, which will have a little bit more writing, maybe some of the harder stuff. The final exam is entirely take-home. For assignments, you can rewrite assignments as long as you turn them in on time. So, a lot of people take that, and through the course, they think of their goal when they get a new assignment is to at least develop like a decent first draft to be able to turn in on time. In order to rewrite a problem, you need to have attempted it in the first place. So half of your grade is based on stuff that you get a second go on. There aren't rewrites on tests, except that what I usually do is let students pick one problem to rewrite on the take-home test portion, but not be able to do a rewrite on the whole thing. And no rewrites on the final exam because there's just no time. Yeah.
So like we turn it in and it doesn't do well, so you tell us after like a class or something?
You like for the assignments?
Yeah.
So yeah, usually the way like the timing will work is usually an assignment will be due on a Thursday. Maybe not like always, but usually this is how it goes. It'll be due on a Thursday. I give you like a week to work on an assignment. You turn it in. I grade it and get it back to you. If it's due on a Thursday, usually I'm pretty good about getting it back to you next Tuesday, And then you have, so I write comments. You'll get it graded. It'd be like just as you don't have to rewrite anything if you're satisfied with your grade. But you'll get it graded and back, and there'll be comments and suggestions for improvement, and then you get a week to submit a rewrite. Yeah. So there are drop-in help sessions. I've got office hours like Tuesday, Thursday morning, but also some drop-in help sessions. I'm doing the one on, why is this not, okay. I'm doing the drop-in session on, this is ridiculous. Okay, sorry. Hold on, I have to close OneNote and open it. Okay. I'm doing the drop-in help session on Wednesdays, 12:30 to 2 in room 212, and then Thursday 1 to 2 in the same room. Linda Wise is going to do the drop-in session for most of the semester, and I'll take that day over later when she's gone for part of the semester. And then I'm going to create it's not there yet, but I'm going to create like a questions forum in Canvas, so it's, you can post questions there. I encourage you to post questions if you have them. Also, answer questions. Like if you think you have, something helpful to say or some guidance on a problem, I encourage you to share that with your classmates if there's a question there that you can answer. And then I'll check it probably daily to make sure that any unanswered questions have been addressed. So you guys have the syllabus. That's what we're looking at now. The other document that you have is the academic integrity document. And if you've taken a class with me, this is probably not going to be very surprising. I think if you were to come up with a set of rules to govern a class you were teaching, you'd probably come up with something similar. On assignments, it's okay to get help, to work together. I encourage you to get help and work together, like we're doing hard things. That's fine. Turn in an assignment that accurately reflects your understanding. If that understanding came at the result of getting help and working together, that's fine. That's how learning works. And on tests, those have to be done independently, so you can't work together on the take-home test. Obviously, you can't work together on the in-class test either. But this take-home test will be independent. You can't work together, but you can ask me questions, and I encourage you to ask me questions. I always ask people, ask questions early, ask questions often. When people are stuck on a problem, I usually give maybe a little nudge in the right direction, kind of let you go away and work on it a bit and let me know if you have more questions. So it's better to ask questions sooner than later if you have them. Gives you the opportunity to get more help. There'll be a reminder of all of these rules for every time I hand out a take-home test, what's allowed, what's not allowed. On take-home tests, you're allowed to use your notes and anything I post to Canvas, and you're allowed to ask me questions. Basically anything else is not allowed. So you can't work together, you can't, it's not open internet, it's not open Wolfram Alpha or any of those other nice tools. I use Canvas a lot. And I post a lot of stuff to Canvas. You're going to be submitting work on Canvas, so it's really important that you keep your credentials to yourself. Nobody else should be logging into your Canvas account. So after this whole document is 3 pages? It's pretty reasonably, it's a reasonable length. I think I encourage you all to read it in detail. Make sure you let me know if you have any questions. I'm happy to clarify anything. At any time in the semester, you can ask for clarification. And then just go on Zoom and sign the contract. So, Canvas, rather. So right now in Canvas, our home page is set to the syllabus page. Probably by tomorrow, I'll set the home page to the modules page. And then there's a link here that'll take you to a survey. It's just a single yes/no. It takes you a couple clicks to sign the contract. It's the spring semester in Vermont, and so sometimes for folks who have to drive here, you might have a hard time getting here. I want you to make choices that are in your own best interest as far as safety goes. It's always possible to Zoom in. That's by request, so I don't automatically Zoom, but if you need to Zoom into class on a certain day, that's fine. Because it's not a telepresence room or anything, all I do is share my screen, and the sound, you're not able to talk, enable a microphone, but there's a chat window that you could use to ask questions. And then a lot of people submit, just the paper solutions that they're turning in, but sometimes people like to submit their assignments online because anytime there's a due date, like if an assignment is due on a Thursday, the due date is always like by 11:59 p.m., right? So turn it in before midnight. So if you want to submit online, that's fine. It will allow you to create a submission. What I want is a PDF. So I want you to, and just because of the work that we're doing, by and large, most of it is probably going to be easier to just do out by hand. If you really like typesetting mathematics, okay, but it takes a lot longer. So I don't want you to worry about like formatting and LaTeX and whatever, or trying to make Word do anything that's useful. If you just write it out by hand, that's fine. You can scan your solutions, like the copier in the 400 building is a scanner. You can use an app like Cam Scanner or Adobe Scan, or I'm sure there's 20 or 30 more apps out there that'll use your camera to create one. I don't want image files. Don't send me JPEGs or PNGs, please. Also, don't make a PDF. Like sometimes people will send me a PDF, and it's like obviously something that was just an image, like a JPEG converted to a PDF format, but nothing else was done to it. And the reason is because those come through really dark, even if they show up good on the screen. Like if I were to print them out, it's just a page of toner, like just covered in toner. It's really hard to work with. So there's I've got a couple of examples here. So here's one that's not ideal, that it would be really hard for me to use. See how it shows up really nice on the screen? If I were to print that out, it'll just be a page of toner. My ink for my pen won't even work on the page. But I used the same photo. I didn't even take a new photo through the app. I just used a different filter on Cam Scanner. And it shows up like this, which is really nice. High contrast, not a photo. It prints out beautifully. So if you're going to submit online, just please make sure that you're submitting something that is usable to me. Okay. I'm going to ask folks to either turn their phones off or put them on Do Not Disturb so we don't hear buzzing. Or, you know, like it's easy to tell maybe who's popular and has a lot of texts coming in because I just hear lots of buzz, buzz, buzz. So just put it on Do Not Disturb, all right? You can still peek at your phone. I hope that you'll pay attention to the lecture, but at the very least, if we're using devices, let's try to make sure that they don't affect the people around us very much because that can be distracting for folks trying to focus on the material. Also, if you have a question, and by the way, you'll have questions. Like this stuff is interesting and fun and kind of hard. So please ask them. Like, don't be afraid to just interrupt me and say you don't understand something. That's better for me and maybe better for other people if you direct the question to me and to the whole class rather than just ask your partner or your neighbor. Because that can be kind of distracting, just hearing, like, even if you're just asking a question about the material, it just can be distracting to hear mumbling. I'm happy to accommodate any needs you have. Just, visit the Center for Academic Success. You can get that documented. They'll send a letter. But even before that happens, you can let me know. The more advanced notice I have, the easier it is to accommodate. But we're not doing any in-class assessments for several weeks, so I'm sure there's plenty of time. Everything else is take-home based, so usually most accommodations involve extra time on tests in class. I post lots of stuff to Canvas. So every day there'll be like a page that I make for each day, like this one, and it lists what we're doing. And then they'll see a PDF posted sometime after class. So tonight or tomorrow morning, there'll be a PDF of the notes we went through. And there'll be a video. The video takes a little bit longer because I have to render it and then put it up on YouTube. But usually by the next day, or that'll be posted. If you're ever looking for material from a class and it looks like maybe I just spaced on posting it, like email me, email or text. That's fine. I'll get on it. Certainly, it won't be the first time something like that has happened. And speaking of Canvas, so I'll use announcements in Canvas to like communicate with the class if there's something kind of important that I want to alert you to. You could log on to Canvas, regularly and check announcements. You could also, I guess, get the Canvas app that works pretty well. If I post an announcement and you have the Canvas app on your phone, it'll just alert you. It'll send you a notification. So, okay. I think most people here have taken a class with me, but here's just a reminder of how your work is graded. I grade it holistically on these criteria. I see whether it's well executed, well communicated, and essentially correct. I've kind of described what each of these things means, and then here's a kind of rough, general rule for how I assign a grade. If something's A-level work, I don't distinguish between a 90, a 95, or 100. I just call it all 100. If something's B-level work, I call it all 87%, and so on. You'll notice it's not a linear scale from 100 to 87 to 75 to 60. That's fine. When you get something graded back, it'll be accompanied by like a grade sheet, like a cover sheet here. There's a little box for each problem. I'm just going to briefly, quickly kind of show you how I come up with a score. So like, suppose we get you get something back, or some student, gets something back, and maybe this is how it's scored. So first of all, each box, it'll tell you the numerical score, and then how you did on communication. The communication is not a separate part of the score. That's rolled into the numerical points that you got, but that's the part of the grading that people often have a harder time seeing where they where their work stands. So that's just for your information. I take each number and I multiply by this guy right here on the side. This is the weight of each problem. So all the problems would be times 1 or times 2 problems. So I take each number, each score, multiply it by its weight. I add them up to get the total number of grade points. So 10, 20, 27. And then I use this table to see where we're at. So 27 grade points here, that'll be an 85.29%.
That's a B.
Yeah. I do, so like, so I you'll get a percentage, a score that's a percentage. As far as when it comes to calculating like your course grade, I use like the traditional scale of like 60 to 62 is like a D minus, 63 to whatever is a D, and so on. The way that I come up with this table, and not that I'm not going to expect you to explain it, but I just want to be transparent. If somebody got a 5 on every problem, right, we would expect them to get 100%. So if somebody got a 5 on every problem here, that would add up to 35 grade points, and that's why 35 corresponds to 100. If somebody got a 4 on every problem, we'd expect that person to get 87%, and if somebody got a 4 on every problem, that would add up to 28 grade points. So that's why 28 is aligned with 87. The table here will look a little bit different depending on how many total grade points are possible. So I just kind of line up those benchmarks, and then in between each of these, it's linear, so it goes down by the same amount. If you got a 3 on everything, it would add up to 21 grade points, and that's why 21 is scored at 75%. Okay. Does anybody have questions they'd like to ask? Yes.
If I want to find the Canvas app for the smartphone,
Oh, yeah.
search Canvas app. Is it
Like it is called. There's one for instructors and one for students, so it's like Canvas for students. The if you have a hard time finding it, the company that makes Canvas is called Instructure. So you could include that in the search.
Oh, it's a pun.
Yeah. Are you still gonna download it?
Yes.
Okay.
You got a lot more useless apps on my phone.
Oh yeah, probably. Okay, are there other questions? There's a lot of writing to do in this class, like more writing than you're going to expect to find. You'll be surprised a little bit, except hopefully not totally surprised because I'm telling you right now. I'm not lying. Not everything requires a lot of writing, but we're going to do a lot of writing, and we're going to like write arguments to prove statements. I love arguing. I love being able to show somebody that I'm right and they should believe me. So I really like math for that reason. There's a lot of writing like that in mathematics.
You should lead the ethics class.
What's that?
You should lead the ethics class.
Should I?
Yeah.
I'm right about a lot of things. Is that a good like forum for me to show how right I am about things?
Might be.
Okay, cool. So the other thing before we get to the fun part and start talking about logic, I just want to give you a heads up, and I already kind of alluded to this before, but this math course will be different than all the other math courses because it's new. Like, there's like knowing some algebra is going to help, right? Like just having some of those mechanics will help. A lot of like the core concepts that we do will feel really foreign, and it'll feel maybe uncomfortable sometimes. Like, is this math? Like, why is this in math? And that's okay. That's a normal feeling. You're gonna feel frustrated. That's okay. But like, people take this course every year. People take this course. They get through it, and I might even say enjoy parts of it. Like, it's kind of cool. So just don't, if you're feeling frustrated, just let yourself feel frustrated and then try again and ask me for help if you have questions, okay? Do we want to do some logic?
Sure.
Okay. Cool. So we're going to look at propositional logic. A proposition is a statement that is either true or false. It's a statement which we can determine is either true or false. So, like 7 plus 3 is 11. That is a proposition. It's not true, but that's fine. In order to be a proposition, it doesn't have to be true. It just has to be something that we can say that's true or that's false. Red is a pretty color. I mean, I love red. It's probably my favorite color. But this is not a proposition. It's a good color, yeah. You know what? Here's the thing. Red is a pretty color is not a proposition because it's subjective. But if I change it and just said red is a color, that's a statement, right? If I said red is a number, that's a proposition too. It's just a false one, okay? Wood comes from trees, yeah. Wood also comes maybe from other, maybe there's like bamboo wood or something like that. I don't know, but that's a proposition. What about this one? This sentence is false. What?
It's annoying.
This last one?
AI.
That's how you what?
That's how you beat rogue AI.
Yeah.
Just tell them this sentence is false.
Yeah.
Short circuit.
Yeah. So is it a proposition?
Can you demonstrate that it's true or false? I don't think so. I don't think it's a proposition.
Yeah. So what if it's true?
That's false.
Yeah. What if it's false?
It's true.
Then it's
Well,
true.
if it's either true or false, then it is a proposition, right?
No, but like, but what? So I don't think it is like this. So it's a paradox.
Mm-hmm.
If it's true, like if we consider the possibility that it's true, if it's true, then it has to be false.
Mm-hmm.
So that's a contradiction. And if it's false, then it has to be true.
Okay.
So it doesn't have like a fixed truth value.
So it's not a proposition.
So it's not a proposition. It's a paradox is not a proposition.
What if it's something that we're not sure about yet?
Oh, but it could be true or false.
Yeah, say like
Schrodinger's bomb.
someone says that black holes are a portal to the universe. Is that true or false? We don't know yet.
Yeah, but so it's okay that it's a proposition. It's something that could be true or false. We just don't know it.
Okay.
That's still a proposition. Yeah, there's lots of. In fact, if you look through math textbooks, like a big result they call a theorem. Sometimes a little result they'll call a lemma. But these like standard results, like an idea that somebody wants to put forward, they just call them proposition, and then we try to see if it's true. And sometimes we don't know if something's true. It still is like could be a proposition. It still is technically a proposition. Sometimes if there's something that we know that if there's something that has not been determined yet, like we don't know if something's true or false, it's like an open question. In mathematics, they'll emphasize that by calling it a conjecture, but it's still a proposition in this like logic setting. So propositions can be more complex. Like a lot of propositions are in the form like if-then statements. Those are propositions. So here's one that's particularly relevant. Either you turn your homework in on time or you won't be permitted to submit a rewrite. That's an or statement. If I get paid on time, I can pay my bills. Those are both propositions. There's going to be some syntax and notation that we're going to learn. These first two are pretty simple. Little t is true. Little f is false. So a proposition could take on the value t or could take on the value f. P, Q, and R, we use those as variables, like propositional variables. They'll be like a stand-in, like if I get paid on time, then I can pay my bills. Like maybe I call this statement P and I call this statement Q, and we could rewrite this as if P, then Q. So they're just sort of variable stand-ins for like statements, propositions. Parentheses are grouping symbols like anything else, and also you could use brackets and curly braces. They have the same meaning that they would have in like regular algebra, like look here first, like treat this as a block and take care of what's in here before you go elsewhere. The big T and the big F, those are constants. Big T is like the statement that's always true. It's like our one in mathematics. So it's a constant for always true. We'll do some examples where we work with big T and big F, and I think you'll get a sense for what they really mean. And then F, always false. The up caret is and. The down caret is or. And this little guy here, which also sometimes we use the little squiggle instead. They mean the same thing. This is a negation, it just means not. So these last three here, the and, or, and the negation, these are connectives. They can connect two propositions together, and we're going to explain their meanings here. So right here, this is a truth table, and what we're doing is constructing the truth table to understand what negation means, to understand what and means, and what or means. Like how do we and two things together, two propositions, or how do we or two propositions together? Notice that the total number of variables is 2. I've got P and Q. Those are the only propositional variables. So when you start by making a truth table, what you do is you have a column for each variable. And then you need a row for each combination of true and false. So that's why there are 4 rows. And I've already just, they could either both be true. I could have P could be true and Q could be false, or vice versa. Those have to be considered separately. And they could also both be false. Those are all the possible true-false combinations. And then we go row by row to fill in the rest of these. So a negation is just whatever the value, in this, we're finding the negation of P. So whatever value P has, just flip it. So how do we fill out this column? In fact, if I just wanted to make a table for the negation, I'd really just need 2 rows and look at the column for P, right? I've got 4 rows here because I've got those other 2 expressions. So P and Q. In order for and to be true, both have to be true. So how do we fill out this column?
True.
False.
Great. Also
false. So,
And also false?
Yeah, the only time and gets a true is if they're both true,
Not if they're the same.
not if they're the same. Right. All right, the or, that's the last one, P or Q. Or is true if either of the two are true, or if they're both true, right? You have to have at least one true in order to make the or true. Another way to think about that is that the only time or is false is if they're both false.
So it's true, 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 false.
Mm-hmm. All right, let's do some translation. So P is the statement I turn in my homework on time, and Q is the statement I get to submit a rewrite. So let's write out in English the meanings of these. The negation of P, what's that?
I don't turn my homework in on time.
Mm-hmm. What about this next one?
I turn my homework in on time and I get to submit a rewrite.
Mm-hmm. What's the last one?
If I turn my homework in on time, then I get to see the
It's not an if then.
It's an or.
It's just or.
I turn my homework in, I don't get to submit a rewrite. I turn my homework
What?
in, or I get to submit a rewrite.
I turn my homework in or I get to submit it. I'm not saying that this proposition is true. Like, that's how we would translate it. This is I turn in, like, it makes it sound like you better not turn it in on time, right? I turn in my homework on time or I get to submit a rewrite. And the P and Q, that's not an if-then either. Like, neither of these are if-then. They're just saying those, in the middle one, right, P and Q, that's just saying those two things happen at the same time. That's basically, like, what that means. And then the bottom one is at least one of those things happens. That's what an or is. When we're evaluating logical expressions, like, they might be kind of complicated, right? There might be a bunch of stuff going on. Like, we've kind of figured out what the negation and the and the or means, but they could be a little bit more involved, like kind of compound statements. So there's sort of an assumed, like, order of operations, like anything, or not assumed, we're going to talk about it, but anything in parentheses is evaluated first. Just like in regular algebra, you know, like we see grouping symbols, we say, oh, I'm going to look there first. Then, once you've done that, you negate anything first. If there's a negation, you got to do the negation first, unless that occurs outside parentheses. But you got to negate a thing first, then you do and then you do or. So, in example 1.3, we want to explain why not P and Q is different from not P and Q.
The second one's a group.
Right, so we could see, like, typographically how they're different. Like, there's some grouping symbols. How would they be interpreted differently?
You're assessing the value of P and Q and then not
PEMDAS.
Yeah, it's sort of like PEMDAS. We don't have any exponents, but yeah, we're assessing the value of P and Q, and then we're
and then
negating
nodding
it.
versus nodding P and then assessing it against.
Q, right, and then sort of anding it together with Q. So think about when each of these would be true. All right, when each of these compound statements would get a true.
Yeah, so the one with the parentheses, we get a true if they're both false.
Okay, so hold on, let me do that first. So you're saying this one is true when they're both false. So this means,
Or if one of them is false, either way, because it's an and, so you just need the answer to be false, and then that gets knotted to true, right?
this means, let's see, P and Q is false unless they're both true, right?
Yeah.
Yeah.
So this is,
'Cause they'll
without the
both-
negation, that means they are both true,
Yeah.
right? That's the only time it's true. It has to be true, true.
Mhm.
And then we're negating it. So,
It's just false.
so it's false. Yeah, so it's true whenever they're not both true.
Yeah, that's what I was.
Right, okay, yeah. Means P and Q aren't both true. Right, like, or let me do this, I'll add a parenthetical. At least one is false, right?
So what we're trying to do is we're just trying to get the answer to be true, right?
Yeah, well, like, sometimes that's how I figure out whether two things are the same or what the difference is, like, are these, when I'm looking at two expressions and I'm trying to figure out how they're the same or different, right? What I really do is consider what is required to make this true? And then, like, usually that helps me answer the question.
Yeah,
Like,
that's
what does
what I
this
tried
mean?
to do that.
Yeah. It's hard, like when you're making logic statements, like I feel like sometimes I go in circles, but, so that's what that one means. And then not,
I'm still stuck on that first one.
okay.
So negate, doesn't that just flip whatever the value is?
Mm-hmm.
So if one of them is true and one of them is false,
Then the answer is false, which gets switched to a true.
Mhm.
After you switch it.
Like, I'm going to go back to this previous page real quick. I'm going to add, so we've already got this here, right? We're just going to negate that.
okay.
So let's flip each of those. So we get false, true, true, true. So the statement that we're looking at is true as long as at least one of these is false. Like, they can't both be true. That's the only time this is false, right? If they're both true, then this is false. So what this sort of means, like the conditions that make this true, is that at least one of these two propositions is false.
Okay.
What about this one without the parentheses? What does that mean?
And the negation is only concerning P,
Mm-hmm.
not Q.
It means the answer is going to be false unless if P is false and Q is true.
So this means, yeah, so it means that P has to be false and Q has to be true. So it's really kind of specific. So P is false and Q is true. Like, those are the conditions that have to be met in order for that to get a true. Let's go back up here again. Let's make a row for that. So not P and Q. Okay, so this time, there's our not P column and our Q column. So we're anding these two columns together, and the way we and columns together is they both have to be true. So that's here
And nowhere else.
and nowhere else, yeah. So we'll have a false, false, true, false. So now look at this. Look at these two columns that we just made for these two statements. That in itself demonstrates that they're not logically equivalent. They are true under different conditions. So we can sort of see, we can use a truth table to see if two expressions are logically equivalent to each other. The only time they're logically equivalent is if they're true row for row, like the columns are totally identical. That's what it would take for two expressions to be logically equivalent. So let's do that. Let's do a more interesting one, maybe, or at least a more involved one. We're going to show that and distributes over or. So we're going to show that these are logically equivalent, these two expressions here. So we say and distributes over or. So just think about how multiplication distributes over addition. So I'm taking the P and Q first, and then bringing over the or, and then P and R. Much in the same way that multiplication distributes over addition in regular algebra. We're going to show that these are equivalent, and there are three variables. So notice I've allowed for a bunch of columns here. If there are three variables, we're going to need 8 columns, or 8 rows rather, in order to allow for all the true-false combinations. So the first thing I'm going to do is I'm going to look at P and Q. So we had true, 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 false, false, true, false, false. You could put them in any of these rows in any order that you want, but I kind of have like a system that I use to make sure I've got them all accounted for. So I need 4 rows for 2 variables, right? For 3 variables, I need 8 because I could have this 4 row, these 4 rows, and that could be a scenario where R is true for all of them, and then I have to repeat them again because R could also be false for all of them. And that'll give me all the possible true-false combinations. Also, if you get annoyed at making little t's and little f's and trying to make sure that they don't look like each other, some people will use 0s and 1s, and that's fine, like 0 for false and 1 for true. So they say R could be all true, R could be all false. So that's how we always start. If we're constructing a truth table, we're going to start by making sure we have all possible true-false combinations for the variables. Now we're just going to work row by row, and you'll notice I didn't just make this column and this column. Those are certainly there, but I'm making columns that I'm going to use to kind of build up to them because I don't want to have to do too many logical steps in one go. So I've made a column now for Q or R. That's a piece of this expression here. So we can fill that in. And then so I'm going to OR the Q and R columns together. And once I have that column, I'm going to AND it together with the P column. So anytime when I'm working through this truth table, I only ever need to compare 2 columns at once. It makes it a lot easier, and I make fewer mistakes that way. So let's fill in the Q or R. So we're going to OR together these 2 columns. What makes OR true, or what makes OR false? What's the easiest way to kind of fill this in?
At least one of them would be true.
To make it true? So let's fill this in. Who wants to?
True.
True.
True. True. True. True. False. True. False.
Great. Perfect. Now we're going to AND that column together with the P column. How do we do that? What needs to be true in order to put a true in this column?
Everything.
Everything?
Everything must be true.
Okay. Like all the columns have to be true, or?
Yes.
No, it's just what the 2 blue highlighted.
Right. So just the 2 blue highlighter, because I'm ANDing these 2 things together.
Yes.
Right, so
Sorry,
I-
I wasn't clear. I didn't mean
Yeah.
we weren't counting the columns.
Okay,
like
okay.
Q and R.
So yeah, so just those two columns that are highlighted. What do we do? Who wants to help fill this in?
True. True. False. False. True. False. False. False.
Yeah, they're both false.
Not sure.
False? Okay, so we have one of the columns now.
The first half of the
Let's do the rest of this now. So now the other side, I'm ORing two of these things together, so I'm making a column for each of these. For each of these two ands, right? And then I'm going to OR those together. Again, when I'm filling this in, I'm hoping that I only need to compare two columns at a time when I'm filling in this table. P and Q. And gets a true only when they're both true, right? So it'll be a true. Where else does it get a true? Down here? Anywhere else? Okay, so the rest of them are false. P and R, so we're going to AND those two together. So both P and R have to be true in order for this to get a true. Otherwise it's false. So that would be the top one, for sure.
and the one right below it.
Yep.
And I think all the rest are false.
Yeah, because at least one of them is false the rest of the time. Great. Now, because we kind of included these kind of builder columns, I guess we might call them, I only have to compare these two now to fill out that last one. Which, you know, when I think about it, I would be hard pressed to just fill in the last column looking only at the three columns that we started with. Like that would be a tough task for me. But it's easy since I built those other columns. So now we're going to OR these together. So we're not ANDing anymore, we're ORing them.
Which would be true,
Mm-hmm.
true, false, false, true, false, false, false.
Yeah. Okay. How we doing so far? Pretty great?
Got that good eye.
Okay, now we're not quite done this one. We finished the table, but look, it said construct a truth table to show that these two are logically equivalent. So what we want to do now is just observe that row for row, these columns are identical. Right? True, true, false, false, true, false, false, false. That's what allows us to say that these are equivalent. Now, I want to just emphasize or like take a moment. A lot of the work we did was in filling in the table. But when we are like presenting a solution or turning in a solution, when the problem says, illustrate that they're the same by blah, 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 blah. Like you want to do that last step. You want to say, I know they're equivalent because these columns are identical. Like
Because that's communication.
That's communication. And just, this is generally true, probably for any class. The less work the reader has to do, like the more work you do to kind of lead the reader through what you're doing, the better. The less work the reader has to do, him or herself, in order to kind of tie up a loose end or something, the better for you. That's probably true in most courses when you're turning in some work. But it's especially true in this course. We want to communicate well. All right, some important facts about logic. And or are commutative. That means that the order doesn't matter. So like P and Q is equivalent to Q and P. And P or Q is equivalent to P, Q or P. They're also associative, and associative is all about grouping. So, so consider the expression P and Q and R. Like I'm anding three things together. If I'm filling out the truth table and I'm trying to make sure that I only have to compare two columns at a time, the fact that it's associative, what that means is that it doesn't matter if I make a column first for P and Q and then and that column together with R, or if I make a column first for Q and R and and it together with P. Notice it's all ands throughout, like it's not different operations. The same is true with or. I'm going to skip 3 for a second. For 4, that's the one we just showed. And distributes over or. So that means that P and parentheses Q or R is equivalent to P and Q or P and R. And I kind of talked about how it's similar to how multiplication distributes over addition. With logic, each operation distributes over the other. So if we go look at item 3 here, or distributes over and. So P or Q and R is equivalent to P or Q and P or R. Big T is an identity for and big F is an identity for or. So I'm going to show you like what. So what that means when something's an identity, it means it won't change the value of something you combine it with. So if T is an identity for that means that if I take any proposition P, if I and it together with big T, that's logically equivalent to P. Like if I made a truth table, it's just whatever the truth is for P, if I and it together with T, it's not going to change it. F is an identity for or. So any proposition F, if I or it with the statement that's always false, that's going to give me something logically equivalent to the statement I started with, to P. And let me just really quickly kind of identify what I mean here. So P could be true or false, right? Big T is the statement that's always true. And if I take a proposition and it, if I and these two together, what do we get?
Whatever P is.
Yeah, true, false, right? You got a T, true and true is true, false and true is false. This column is identical to that column. That's just what this means. Like big T is just the statement that's always true. So if you make a column for big T, it's just trues all down the whole column. F's is false all down the whole column. So we could do something similar here. The or gets a true at the top and then a false down here. And so these columns are the same.
What if you or true or and false?
If you or true, it's true, true. like, and with true, only one thing has to be true in order to make it true.
Yeah.
So if you have a column that's all true, if you or anything with that column, it's going to be all true. If you and something with false, in order for something to be true, they have to all be true. So if you and something with a column that's all false, the and is going to be false because there's not ever an instance where they're both true. And then the last one, P and not P is logically equivalent to false. That makes sense. P is either going to be true or false. It can't be both. So if you and a proposition with its negation, it'll be false. If you or a proposition with its negation, it will always be true. Like P either happens or it doesn't. P is either true or it's false. It's got to be one or the other. So if you and something with its negation, it's going to be true. True, true, true. There's another really important connective that we haven't done yet. It's the implication, the if-then, or implies. So, like P implies Q, this little double arrow is implies. That's P implies Q. It's the same as saying if P, then Q. And here is the meaning of implies. So we have two variables, which means I need 4 rows, right? Here are all the true, false combinations. The implies, P implies Q, the only time it gets a false is if P is true and Q is false. All other times it gets a true. Basically, if P is true and Q is true, then P implies true. P implies Q is true. If P is true and Q is false, P implies Q can't be true, right? If it were true, then whenever P is true, Q would have to be true, right? So that can't happen. Now for these rows where P is false, it gets sort of by default a true. We can't say it's false. The predicate, the premise isn't met. So drawing a conclusion, if P is not true, Q can do whatever it wants. Right? Like, that's what the implication means. The premise is not being met. So the example I like to use is like, suppose somebody tells you, in this statement it's mom and dad, but whoever says, look, if you get all A's this semester, I'm gonna buy you a car. Okay? So there's an if then. So our P statement, I get all A's. Our Q statement, mom and dad buy me a car. Consider these possibilities. If I got all A's and also they ended up and mom and dad did buy me a car, did they keep their promise?
Yes.
Yes. So they kept their promise, so the P implies Q gets a true. If I got all A's and they did not buy me a car, did they keep their promise?
No.
No. So this gets a false. What if I did not get all A's, but like I got like a B plus and it was an awful class and maybe I was sick for a month and I still pulled off a B plus and mom and dad decided I'm going to buy you a car anyway. Did they keep their promise, or could I say that they lied when they told me if I got all A's they would buy me a car?
They never said they wouldn't buy you a car.
Right. They're under no obligation to buy me a car if I don't get all A's, but they can do whatever they want. If I don't hold up my end of the bargain of getting all A's, they can do whatever they want. So yeah, they kept their promise because they could do whatever they want at that point. There's no way I could call them liars if I don't get all A's. So this gets a true here. If I don't get all A's and they don't buy me a car, yeah, they still kept their promise. Oops. True. True. One quick note is that when we're evaluating an expression with an implies, we always evaluate the implies last. So we do one side, we do the other side, and then we see if then we do the implies part. Okay. A couple more truth tables to do to finish out the day. We have both of these just involve a couple of propositions. So these tables have 4 rows. So the first thing I need to do is just fill in the first 2 columns, right? All the true-false combinations. So true, 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 false, false, true, false, false. All right, what about not Q? How do we fill that in?
Opposite of the Q column.
Mm-hmm. So we get false, true, false, true. What about P and Q?
Both P and Q are true.
Right, so the top one's a true, then all the rest are false, I think. Okay. Now we want to apply the implies from not Q to P and Q. And I'll just point, like I set up the columns in advance, right? But let's say I was doing this problem and I had to like just make my own table. I find it, the implies, like the order matters, right? Like P implies Q is different from Q implies P.
So when you're creating the table, put the
Yeah, I mean, you could do it either way, but like my brain, when I'm looking at it, I just have a hard time.
precedent.
Yeah, I just have a hard time making my brain think about it backwards. So I put this first for that reason. It made it easier for me. So, what is the only time the implies gets a false?
When P equals false and Q equals true.
When, let's see.
Yeah, when Q, not Q is true. No.
So, well, when just the imply, so I'm gonna forget about the not Q or anything, but like P implies Q, like the left side implies right side, right? The only time it gets a false is if I have true implies false, right? Like, so for this middle row here.
Okay.
So for this one, this will only get a true when not Q is true, and the P and Q is false.
It's the same spot as the second column.
So say that again.
Or second row, because true,
Uh-huh.
true implies false. That's the only time it'll get an F.
I think the bottom row too.
Oh, there it is right there.
Yeah. And then the others,
True, true.
true.
This is the true, true.
One more. We're going to construct a truth table for not Q implies not P. So not Q, I'm just going to copy that from above. False, true, false, true. And then not P.
False, false, true, true.
Great. Okay, now we're going to do the implies.
Not Q implies. So, true implies false. This time it's only in the second row.
Right. Notice, this was the same. If I did, let's just copy that, the one from the previous page. P implies Q. Ah. Okay. So P implies Q. Now if I'm doing it with the ones that were highlighted in blue here, false implies true is only the second row. Like that. So look at these 2 columns.
They're the same.
They're the same. So what does that mean?
Commutative.
Not commutative. Commutative means I can reverse the order.
Or-
Nope.
wait, no, not-
The negative of the opposite.
that's like-
They're what?
The negative of the opposite is equals to.
Yeah, like they're so they're identical columns. That means
It's like comparing absolutes.
maybe. I mean, I guess what I'm going for is just say like they're equivalent statements.
If we
There.
make them negative, and
Oh, and then flip.
and flip
Yeah,
it,
that's yes, exactly right. So taking the negation and flipping the order, right? Not Q implies not P versus P implies Q. They're logically equivalent. This is an important observation to make. In fact, we say that the expression not Q implies not P. We call it the contrapositive of the statement P implies Q. It's important because we're gonna write a bunch of proofs. In fact, on Thursday, we're gonna start writing some proofs on Thursday. It's gonna be great fun. We're gonna see, like, sometimes, like doing an if-then proof, sometimes we just one way to go about it is to do it directly, like assume the if is true, right? And then show that the then has to be true. That's a really direct way to go about it. Sometimes that's really hard, but if I just make the contrapositive, doing it in that direction is a lot easier. So, like, knowing that they're logically equivalent is helpful because it gives us a tool, gives us another option if proving something directly just is kind of a bear. So we're gonna do that on Thursday. I hope you all are looking forward to it. We'll probably spend Thursday and maybe even part of Tuesday doing some of that proofreading. Until then, sometime this week, make sure that if you haven't done so already, just read through the syllabus. Also, that academic integrity contract, make sure to just read through it and jot down any questions you have about it. Let me know if you have any questions this week. Get up on Canvas and sign the contract. I'll see you all on Thursday.